really well. I think the average was a 91. Maybe that's too high, but um, most 200 level courses don't even teach logistic regression. And there aren't many 400 level courses here that teach logistic regression. So I'm really glad that people understood it so well. So let's go over it. All right, so let's start with this first page here. And so this first page was on transforming data, and it said which transformations would not work. So those three would not work. And let's see, then this looked like the square root, and that looked like the log. And for this problem here, I'll just go over it quickly because people did so well. So stop me if you want me to explain anything. But here, what did we do? We just plugged in 1 million for the population, and then that's e to the, so that answer is 5.27. And then you just exponentiate it to get 194. And then you wanted to do a confidence interval. Error bars around the area, not the log area. So that would be, you're adding this standard error plus or minus 2 times 0.75. So that would be e to the 5.27 minus 1.5 to e to the 5.27 plus 1.5. So there's the limits right there. That's the confidence interval for the log. But then when you exponentiate it, you get these asymmetrical confidence interval. And let's see, for this one, you just had to see that the geometric mean, that the estimated area is the geometric mean of the endpoints there. So questions on that? Okay, let's go to the next page. Whoa, this looks terrible here. I had to darken this. Let me show you this. All right, so this question 2, this one right here, was only worth 1 point each instead of, I originally had it 2 points, just because so many people didn't understand these directions. It says each plot will be the answer to exactly one of the questions. So in other words, these 6 plots, these 6 answers will be distributed among these 4 questions. So there should be 6 circles here. Circle 6 of these answers. So so many people somehow either didn't read that or didn't understand it and didn't follow those directions. So we just decided to make them worth 1 point each, and this is what it looks like. Any questions on this? If you have questions on your own, just come see me, okay? And then, let's see, now we can go back to here. These were 2 points each. I just want to make sure it was graded correctly for everybody. And let's look at this chart here. Most people did this one very well. You had a lot of practice. I think that those practice tests, or especially when you do, we have tons of practice on computations, is very helpful. So you had a lot of practice on this. And I think most everybody got this one. All right, just make sure yours was graded correctly. And let's go to the next page. All right, so for this one, females are more likely. Estimated odds ratio was e raised to 1.4 for gender and e raised to 0.82. So those 2 numbers there. And sorry, this is kind of light, but let me show you what the answer, maybe if I darken the answers a little bit. This, you just say, you exponentiate that, and you got this. And then 0.74 over 1 plus 0.74. So that's what that looks like. Any questions on any of this? If these 2 columns we gave continued error for. Whatever you had here, if you made a careless error here, if you just did the method right, we gave continued error credit. But most people got this pretty well. And the answers were here was 10.37 and 8.66. All right, now let's look at the multiple choice. two males have a 3-point difference. Compare their odds of getting into medical school. Okay, so for each point, that was the odds ratio right here is 2.27. So it's 2.27 times 2.27 times 2.27. It would be the same for females. Then the probability, there's not enough information here. These last two is where people had some problems, so just let's quickly look at them. It says a female has a PS score 1 point lower than a male. How do the odds compare of getting into medical school? Well, she's favored because she's female, so that's 4 multiplied by 4.06. But then 1 point lower, so instead of multiplying by 2.27, you divide. So that's your answer right there. In this one, some people, okay, the odds of a female getting into medical school are the same as the odds of a male getting in. When? Well, some people just realized that was this problem right here. I didn't even see that. You know, here it's 10.37 versus 8.66 right here. When the female has a 1.71 lower score. Because you just did that problem. So a lot of people saw that. I didn't even think of that. I thought you would just set the equations equal here, the log odds equations, and you know, here for female and here for male, and just solve for the difference. But some people just did it really quickly this way. Any questions on that? Okay. Lots of people didn't get any points here. It was worth 2 points. I don't know what. They just did the arithmetic all wrong. It wasn't a careless error. I'm just not sure what they were doing. They might have started off with the right idea, but somehow just got tangled up. So a lot of people lost a full 2 points here. All right, now the next one was just, I hope people, was 2 points for each of these, just 3 degrees of freedom, and this was the slope over the standard error here. Okay, I think everything, this is the only one that people, on this one, lots of people got wrong. And I think it was just that the wrong answer sounded so reasonable. You know, do you think it makes sense to do a two-sided t-test for GPA and PS scores? I don't think it makes sense because, you know, the null hypothesis, the alternative hypothesis would be that if they matter at all, of course they're going to matter in the direction of, you'd know the direction. You'd know that a GP, if they have an effect, you'd know which direction it would be in. No one's going to think that a lower GPA is going to help you get into med school. So, or a lower MCAT score would, no one would think that. So you know which direction. So I think the problem is that I tend to write the wrong answers in this sort of, in a way that sounds good. It's very easy. It's much easier to lie with words than with statistics. People always say you lie with statistics, but it's so easy to just, if you just write without thinking, the words just can spin out and sound good without meaning anything, and that's what I did here. I said, yes, since higher GPA and PS scores are likely to increase the probability of getting into med school, you know, that's why you'd want it two-sided, because then lower ones are likely to decrease. Well, that's still one-directional. You know, obviously the higher the scores, the more likely you'd get in, and the lower the scores, the less likely. That's still that same direction. So it's just, that's just bullshit. It's just, I mean, what's the word? I mean, just, well, that is the word. Just saying stuff, you know, it doesn't mean anything. All right. Okay. And so now let's see what else. So compute a 95% confidence interval for the slope, for the physical science score. So you just, it's just, there's the slope. And I said to just take plus or minus 2, use 2, plus or minus 2 of what you were given here. And you get these limits. And then if you want to then do the 95% confidence interval for the odds ratio, you just exponentiate and get that. So that's pretty much it. And let's turn the page. And this last page, people did phenomenally on. So proud, so great. He's very happy. So, very important, and you all did great on this page. So, any questions? So now what's left for, we just have this one section left, and we're going to finish that up this week. The homework's already posted. So you're going to be good. So the final is cumulative. I know people aren't real happy about that, but it's the best way to learn. I mean, it's hard enough to retain information. You know, people can learn for an exam and then they forget it all. Without a cumulative final, it's pretty hopeless that people would retain much. So I just like to give cumulative finals. So the best way to study would be to go over the 3 exams, and the 3 exams we've already taken and the practice exams online. And then for this section on non-parametric tests that we're going to spend this week on, and maybe half of one class next week, I'll give you a whole bunch of practice problems for them online where you can do them multiple times with different numbers. These questions, I think you're going to like this section, so let's just dive right in and finish it, and at least do this first non-parametric test called the Wilcoxon-Mann-Whitney rank sum. And the homework that you have due Wednesday is on this chapter. So you can even do it during class if you like. It's posted now. All right, so the difference between parametric and non-parametric tests, what is that? Well, the parametric tests are based on certain assumptions about the distribution that our sample data comes from, right? All these significance tests are testing whether some difference we see in the sample reflects a true difference in the population or not. And the parametric tests all are based on certain assumptions about the population distributions that the sample comes from. And the non-parametric tests, like the re-randomization test that we've already done, that's a non-parametric test. And what these ones are rank tests. These tests do not depend on any assumptions about the wider population. Nothing about the distribution of the wider population. So they're more applicable to more situations. So, now in part 7, we saw how if we could sometimes, if it looks like our data, you see, most of the tests we've been doing, except for the randomization, assume that either we're dealing with normal populations or statistics that follow normal distributions, or the sum of, it pretty much always goes back to something following a normal distribution or a big enough sample size that the central limit theorem kicks in. And then in part 7, we saw how we could sometimes transform data with lopsided histograms into data looking more normal by, we looked at these power transformations going up or down the power ladder. That was what we just looked at in our exam. But what if we can't transform the data to something normal looking? Well, we have 2 options. One is the option we've already done, which was the re-randomization test that we've looked at, where we let the computer randomly sample all possible samples under the null and see how likely it is to get a sample as extreme or more extreme as the one we got. These are all significance tests for testing what's called the strict null, that some population parameter is 0, or the difference between 2 or more groups means is 0, or the correlation coefficient is 0. In other words, that looking at what a random division of would look like, of a set of numbers, into 2 or 3 groups. You're going to see differences, but are the differences going to be, and you look at the sampling distribution of that under the null and see how big the differences you got in your sample are compared to what you'd get from just some random division into multiple groups. Okay, now, so we've done that with the re-randomization. Now we can transform the lopsided data into more regular looking data by replacing values with their rankings. That's what we're going to do. So all the tests that we're going to look at are, instead of looking at the actual values that we get, we are just going to replace them with rankings. That's all we're going to do. So if we had a data set of 20 numerical values, we just list them from smallest to largest, from 1 to 20. And you'd have the integers 1 through 20, and then we work with those integers, which are much easier to work with and will obviously follow, the statistics will follow the normal curve much quicker, because you're not going to have any, they're very just uniform distribution between 1 and whatever, and so the mean of that and all that will follow the normal curve much more quickly. So that's what we're going to do. Okay, so there's going to be 3 tests we're going to do, and today we're just doing the Wilcoxon Mann-Whitney test, which is equivalent to, it's just comparing 2 group means. So it's an alternative to the 2-sample t-test. And then we're going to look at this next one. Next time we'll look at these 2, and this one's an alternative to when you're comparing more than 2 group means. So it's an alternative to ANOVA. And then we're going to look at a correlation coefficient that's computed by replacing all our values with ranks and computing the correlation coefficient on the ranks. And that's an alternative to our usual correlation coefficient, R, in the hypothesis test we've done with R. So let's start here. Okay, so the rank sum test. This is very widely used, and basically what you do is you combine all your data into one ordered list, and then compute and rank it, and then compute the sum of the ranks for each group. Much easier. You can read this, but let's just go straight to the example, and you'll see what I mean. All right. So this is our first example here. So we're on page 156. Okay, 156. So let's look at this. It says 2 different forms of the final, A and B, were randomly given to a group of 15 students. All right. This actually comes from real life. All the years I taught Stat 100, I always had a few versions of the final, and I was worried that they might not be equivalently, the one might be harder than the other. So I'd like to give it, there would always be a group of students that wanted to take it early, so I would always do this. So 2 different forms of the final were randomly given to a group of, let's say, 15 students, and 7 got form A and 8 got form B. And here are the scores of the 2 groups. Okay, so group A, the scores, I put them in order here, and I put group B in order. Now, it would be problematic to do a 2-sample, these are small samples, so you'd think, oh, could we do a t-test? But I pretty much know that my finals are not normally distributed. I mean, they have a long left-hand tail. Look at that. And they're sort of bunched up towards the high end, like all our exams. And so doing a 2-sample t-test would not be valid. So another alternative would be, and we have a too small a sample for the central limit theorem to kick in, so it's better to do a ranking test. And so the null hypothesis for the rank test, this Wilcoxon Mann-Whitney test, is that there's no difference in difficulty between the 2 exam forms in the population for any segment of the population. Not just that the means are the same, it's actually a stronger hypothesis. It's not just saying the means are the same. It's saying that there's also that the distributions are the same. This is stronger than just saying the means are the same. It's more like saying every percentile is the same. Because I wanted to make sure that it wasn't just the overall mean that was the same, but I wanted to make sure that like the tests were equivalently difficult for the people at the low end and the high end and throughout. So this was actually a better choice of test statistic. And the alternative hypothesis is no, the exam forms are not the same level of difficulty for at least one segment of the population. So it probably makes sense to you too. Now I randomly assigned them, pretend these were really the results I got. Do you really think that look at this 11. Now somebody who gets an 11 on one of my exams isn't getting an 11 because the exam's too hard. I mean, because if this person was put in group B, they'd probably get an 11 too. This is somebody who's just probably not answering half the questions, should have dropped the class, and you can see why replacing these actual scores with their ranks might make more sense, because this 11 is going to weight down this average so much, right? Whereas if you just replace them with just say it's the lowest score, then it would make it would be equivalent to, what's the lowest score besides that, 60? Then it would be like getting a 59. You see, the rank test if I replace this with a 59, it would be exactly the same as getting a 0. It's just, you're just going to do rankings because 11 is the lowest score and so would 59. The second highest is 60. So let's see how this works. So you can understand why it would make sense to do it in certain circumstances. So what we want to do is we want to combine the group into one ordered list, ranked from 1 to 15, because there's 15 numbers together. And if there are any ties, give the average of the ranks. All right, so let's see how we do this. So this is the lowest one, so that gets rank 1. And we can just look, and the next lowest is 60, so that will get rank 2. And there's enough ones there's a few enough scores, we don't have to arrange them in order, we can just eyeball 1. 65 is the next one, right? There's no more 60s, so now you might say, oh, you give a 4 to 70, but wait a minute. 4 and 5, it's taking up 2 spots, a 4 and a 5. So what we do is they get the average. 4, instead of giving one a 4 and one a 5, they both get 4.5, which means our next smallest score, which is what? After 70, our next smallest score is 75. Do you think we should give that a 5? You'd think it, right? Don't make that mistake. You don't want to give it a 5 because basically you already used up that spot. 1, 2, 3, 4, 5. We have 5. Now we're on to number 6 spot. So we have to give this a 6. Do you see? That's a very common mistake people make. They'll give it a 5, don't. All right. Now let's see. 7 would be 7 would be right here, right? 79, 7. And now our next one is 81. So that would be an 8. And then we go over here, 9, 10. Tell me if I make a mistake, okay? 10, 88. Isn't this 11? And then 12 is over here. 13's here. 14's here. And you have to end up at 15. Okay, you'll know you made a mistake if you did that. If you gave this one a 5, you'd know, because you would end up at 14. You wouldn't end up at 15. The last number has to be, you go from 1 to 15, unless the last number's a tie, I guess. All right, so that's our rankings. Now what we do is you just sum up the rankings for each group. Now you really don't have to do both groups because you're going to see once you get one, you'll know the other. So I would just start with the smaller one because it's easier to do. 7 numbers in here, so you just add them up. 1 plus 4.5 plus 6 plus 9 plus 10 plus 12 plus 14, and you add all those up, and I got 56.5. So that's called the rank sum for this group A. I'm using R for rank sum. Now I could do the same thing here. I could 2 plus 3 plus 4.5 plus 7 plus 8 plus 11 plus 13 and plus 15. But an easier way to do that, instead of doing all that, is to know the relationship between thinking that the together, the rank sum of this one plus the rank sum of this one has to equal this formula right here. Adding all the numbers together is this formula, and probably some of you recognize that as the sum of the numbers just from 1 to n, right? It's a famous story connected with that. But first, let's just look at why that would be true. So right now, we're looking at the sum of the numbers between 1 to 15. N's 15. So you go 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10 plus 11, 12, 13, 14, and 15. So instead, can you see why this might be true? Here, let's look at this. Hold up. All right. Now, watch. This n plus 1, in this case, let me just write down what this is. So we have 15 times 15 plus 1 over 2. All right. So think of it this way. You start at both ends, so 15 plus 1 is 16, right? And notice 14 plus 2 is also 16. And 13 plus 3 is 16. And 12 plus 4 is 16. 11 plus 5 is 16. So the n plus 1, you just think, oh, the 16. How many 16s do we have? Well, we have, how many 16s do we have? We have n over 2 16s, because we're just going to go halfway. We have n over 2 16s. So for example, so we have this, 1 plus n is 16. And then our next one, 2 plus 14, 16. And how many do we have? N over 2. So this is 120. Another way you can think of this is that 8 is right dead in the center, so it's the average, right? 8 is the average right here. That's 16 over 2 is 8. So this part right here is the average. So you can think of, oh, how many, 8 is the average. So basically, and that's going to be one above, that's going to be one below. So you could just take whatever the average is by the sample size, because it will average out. You're going down 1, you're going up 1. So basically, you have, if you had replaced this with all 8s, it would be the same thing. That's another way to think about it. Okay. The famous story, it's a funny story. It's about Gauss is a little, the Gaussian curve, right? Normal curve. So Gauss, as a little boy, I guess, got bored in school a lot, and his teachers tried to, give him busy work. And so once the teacher said, okay, add up the numbers between 1 and 100, and the teacher thought it was going to take Gauss a long time, but Gauss thought, 100 over 2, that's 50 times, he just did 50 over 101 times 101, just did it really fast. Isn't that pretty amazing? Yep. So he impressed his teacher, and it's pretty cool. So that's an easy way to remember this formula. You should remember it. Okay. And now, so I said, okay, so I know it all adds up to 120. So this plus this has to be 120. So I could have added all this up directly. Or another way to do it is just to say 120 minus 56.5. And you'll get 63.5. But I would check just to make sure that this is 63.5. Check it. Okay, so that's the rank sum for both of them. Now, so now because these numbers are just so uniform, so just the integers between 1 to 15, the rank sum is going to follow the normal curve pretty quickly. There's not like, it wouldn't necessarily, if you had, if you have really weird numbers, it's going to take a lot longer to follow the normal curve, the sum of the numbers. But these are going to follow pretty quickly. Remember we learned, the probability, the probability histogram for the sum of, draws from end draws is going to look a lot like the normal curve as long as the draws are big enough, but it's going to converge to normality much quicker in sort of uniform if it starts off with very even distribution. So that's why this is so handy, is that it doesn't take long before we know that we can actually figure out the exact probability distribution with small samples, but as soon as they get about both bigger than 6, you can just use the normal curve, the normal approximation. At least for the purposes of this course, once it's 7 or more in each sample, you can use the normal approximation. So why don't we do that? So we can use a z-test, and then we'll look at, first let's just do this. So we can use a z-stat to test the null, since for large enough group sample sizes, here we have 7 and 8, they're both greater than 6. The probability distribution of the rank sum for each group is very close to normal when the null is true, okay? And with the expected value and standard error below. Well, the expected value is pretty easy to see. Let's think about what that would be. The expected value for the rank sum for group A. Let's start there. So what would we expect for group A? Why does this make sense? Well, there's 7 numbers in group A now. If it's just a random distribution, there's no reason to think one's going to be better than the other. Wouldn't you expect each to sort of average out to the average? Wouldn't you? I mean, why would one group be higher than you randomly take a group of 15 numbers, and it's just as likely to be above average as below average. So for each number in here is just as likely to be above as below. So your expected value would just be the average of the numbers, right? That the sum of these would be that each one, like this, would be, maybe it's well below, but then you're just as likely to get one just as high above. So when you sum them all together, it would just be n, your sample size, times the average. It's just what we did here. So this is the average. And this, because we're talking about the sum of numbers from 1 all the way through 15, but here we're only talking about 7 numbers. And they're not 1 through 7, they're 1 through 15. So we'd expect on the average, you'd expect the average, and then you just multiply by the sample size. So that's the expected value. Does that make sense? So the sample size is 7 for the group A, and the average is 16 over 2, 15 plus 1 over 2, which is 8. So you would expect this to be 56. All right? That's our expected value. What did we observe? 56.5. That looks really close, but hold on. We have to figure out what the standard error is. How much variability there is. If we did this over and over and over again and took 15 numbers between 1 and 15, and randomly put 7 in this group and 8 in this, how much variation would there be in the rank, in the sum of this rank? So that is given by this formula here. And let's look at what this formula means. First of all, okay, it's the square root of, this is your sample size for your first group, 7, times your sample group for your second group, 8. I mean, think about it. If we put everything in one group, we'd have 15 times 0, and we'd have no variation. The biggest variation will come when there's sort of an even split here, because the most different options. If I put all 15 numbers, you're not going to have any variation. One group will have 0 all the time. So 7 times 8 times n minus 1, which is 16, over 12. And we can talk about where this 12 comes from later on. Okay, so that's our standard error, and of course it's the standard error for whatever variation you have with one group, it's going to be the same. If you divide it so there's 0 numbers here in one group and 12, then you'll always get the same 15 numbers in the other group, so it's not going to have any variation. So whatever variation there's in one group, it's going to be the same for the other. So the standard error is the same for the rank sum of both groups. All right, so now we've got these two numbers, and our z-statistic is always our observed statistic. In this case, it's the rank sum for group A, minus our expected over our standard error. So our observed, what did we observe? We observed 56.5. We expected, if the two exams are completely, there's no reason anybody should do better on one than the other, then we would expect a rank sum of 56 for group A, and over a standard error of, whoops, I didn't tell you what that was, that is 8.64. That's our standard error. So it's over 8.64. And that turns out to be a very, very, very tiny z-statistic, very close to 0. So clearly it's not significant, which is great for me because I would want these exams to be as much alike as possible. So this is what I'd be aiming for. I'd say, yes, they're so close. I can go ahead and give these exams, and it would be fair to both groups. So to get the p-value, I know it's going to be a humongous p-value. We're not going to be rejecting any null here. These exams are about as alike as you can get in terms of the level of difficulty, right? And so, but to get the exact p-value, we have as a z-score, z, we have the normal curve 0, 1, 2, 3, -1, -2, and -3. And we have this 0.06 or 58. It's very close. Let's say we're at the exam and we're just going to go to the nearest line on the table. And, okay, 4. It's right in here. 4% in the middle. We have 0.058. It's very close to the 4% in the middle, so let's just go with that. So I'm just going to put a little 4% in the middle with tiny little error bars on either side. And that is 0.058 is the z-score, and this is negative 0.058. Okay, and so the rest of it, so my p-value is it's going to be two-sided because I didn't know I had no idea which was going to be harder. And my p-value is just going to be 100 minus 4. Not over anything, which is equal to 96%. That's my p-value. Huge p-value. I want as big a p-value as possible. That's great. All right. And by the way, if I put it on the axis of the, this is z, but if I put it on the axis of the rank sum for group A, right in the middle is not 0. Right in the middle is my expected value of 56. And this right here is what I observed, 56.5. Okay? Yeah.
So why did you assume the expected group average for A to be 56?
I did because I thought, okay, I wouldn't expect all low ranks here, would I? Under the null, wouldn't I expect them to be about equal? Like if I took these, I first changed these to the rankings, they go from 1 to 15. And if I just randomly distributed them, don't you think I would expect just as many low scores?
If that's assuming that you didn't have to use the 4.5.
Even if I use the 4.5, it would be okay, because there'd be like, on the average, that's a good question. But let's just think about it without the 4.5, but it's pretty much the same with the 4.5, but that's a good question. So yeah, if I'd expect just as many. See, even with the 4.5, the average is 8 still. So on the whole, wouldn't I expect these the sum of these to be, you can think of it as n times, I'm really taking the sum of this, so it's like n times the average of the box. Remember, n would be the expected value for the sum. Does that make sense to you? N times the average. And here, n is 7, and the average of all of them is 8. Even with the 4.5 there, because you have, think about it, if you have a 4, you could, a 4 and a 5, average out to two 4.5s. Does that make sense? Okay. So now, so it's n, whatever your sample size is, times n plus 1 over 2. That's the sample size. So let's do, okay, so now we marked it, we calculated the p, we did all that. Our conclusion is what? Obviously, don't reject the null. Do not reject the null. Do not reject null. We conclude, this conclusion, which is what I wanted, very happy about, we conclude that the exams are the same level, the two versions are the same level of difficulty. Same level of difficulty. Okay? Now, what if I decided to not do ZA but ZB? How would anything change? So ZB would be the observed rank sum for the B group. What do you think the expected minus the expected? So our ZB was, our observed is 63.5 minus our expected. So what would be the expected? Let's think about it. The expected value, if we were going to do the rank sum for B, would be what? Instead of 7, we would put what here? 8, because our sample size is 8, times, again, the same thing, 16 over 2, so we get 64. So it'd be 63.5 minus 64, and then over the standard error for the group B, and remember they're the same, so we'd use this again, 8.64, and can you see that it's just going to be, the numerator is just going to be the other direction. It's instead of positive 0.5, we'll have negative 0.5 over 8.64. So it's just going to be negative 0.058. So it would just be, if we were doing, it would just be here. We'd get the same P. So compare, so in general, they're always going to be opposites. So ZB is always going to be the opposite of ZA. In absolute value, they'll be the same. So their p-values will be the same. Okay? They'll have the same, all right? And compare the p-values. I should write that. The p-values are same. All right? And their actual z's are just the opposite sign. Absolute value, they're the same. Any other questions? All right. Now that you've seen this, I'm going to show you another statistic that's equivalent to the rank sum, but is used a lot. For one thing, there are handy tables for it, and it's called the U statistic. So let's look at this. And so it's a variation on the rank sum test. And often people use the U statistic instead of the R, or the rank sum statistic, especially because the tables, like on the next page, you're going to see a table for when you have small samples, the exact probability tables. They're always done in terms of U, so you should know how to do these. All right, so let's look at the U stat. And it's the U statistic for group A sums the number of times group A scores surpass group B scores. And the U statistic for group B is the number of times group B scores surpass group A scores. So we're going to do it this time using the U test statistic, which is just another way. It's actually an equivalent way. You're going to get the same Z-scores. It's another way to do rankings, an equivalent way to do rankings, but I'll just say another. You'll get the same answer in terms of p-values. But I think the U statistic is probably very widely used, more widely used probably. Okay, so here we have our same data. Now, what do I mean by this? So you start, it's like two teams are playing each other, and they're having individual matches. Like, let's say they're singles tennis, and you have this group A team and group B team, and each player in group A plays each player in group B, and you count how many times group A players beat group B players for each one, okay? So for example, here's this person who scored the lowest. So this person is playing, did he beat any of these players? No, so he counts as 0, okay? 0 is his use. Now 70, you count how many times 70 beat these scores. Well, 70 beat 60, so that's 1 time. 65, 2, 70. Now there's a tie, and you count ties as a half. So it's 2, 1, 2, and then this counts as a half, 2.5. All right, so 75. How many times does 75 beat these? Well, 1, 2, 3. Just 3, right? Okay, so 3. Then for 85, 1, 2, 3, 4, 5. So its U is 5. 88 is 1, beats 6, 1, 2, 3, 4, 5. Again. They have the same because they beat the same number of people. Now 92 beats everybody except the last 2. So that's 6. And 96 beats everybody except 100, so that's 7. And so this team's U, when you get the U, you'd just add that up. You'd say 0, you'd add all those numbers up, and that would be their U score. Do you get it? Why don't you try this one? Like, why don't you do this one on your own? You'd go here. I'll start you. 60 beats how many? 1. So 60 is going to have a score of 1. So just finish those numbers and see what you get. Get all their U values. You want, and just raise your hand if you have any questions on how to do this. I just want to make sure you know how to do this. Sometimes people get really confused with this U statistic. Okay, look up when you're finished so I know when you're finished. Okay, so let's just make sure you got what I got. So I got a 1 here, 65 beats 1. 70 beats, I got 1.5 because of the tie. 7 beats 11, but it's tied here. Then 79 is 1, 3. And then 3, 5, 6, and 100 beat all 7 of them. So did you all get that? Okay. Now what you want to do is add up to choose. You can choose either group. Now again, once you know one group, you're going to be able to know the other. But first let's add up these. So you have 0 plus 2.5 plus 3 plus 5 plus 5 plus 6 plus 7. And I got 28.5. So that's the U statistic. All right? Now, you can add these up, and probably you should to check. 1 plus 1 plus 1.5 plus 3 plus 3 plus 5 plus 6 plus 7. But before you sum them up, what should this answer be? Let's think about it. Together, they should sum to, think what it is. Together, they should sum to the number in group A, 7, times the number in group B, 8, 56. Because that's the number of possible matches, pairwise comparisons there are. The number of pairwise comparisons. So this should be what then? If you have, you could just do, so UB should be equal to, UB should equal 56 minus 28.5, which is 27.5. So check that it does. It does. Check that. And this is really simple to think about. Sometimes it's just easier to look at the extremes here. So let's say I was playing chess, let's say. I like chess. With you 4 people. So I'm one team, you 4 another team. So how many pairwise comparisons are there? We each plays, I have to play everybody on the team. So I play 4 people. So and you can only play me. So there's 4 times 1 pairwise comparisons, correct? So let's say I'm terrible and I lose every one. Then I'd get a 0, right? And each one of you would get 1. So that would sum to 4. And the opposite, let's say I beat all of you, then I'd get 4 points and you'd all get 0. And the expected value would be what? The expected value would be that I was average, right? I mean, expected value under the null, that we're all just random people, that, right? And so that, we're all randomly distributed, so it would be unlikely. So that I would beat, if I was average, I'd beat 2 of you. And so I'd have 2 points, and together you would have 2 points. So it's sum to. So it makes sense. Yes, what's your question?
I'm adding up UB and equals 28.5.
Oh, did I do a mistake? Thank you for maybe catching that. Hold up. So you added up. Did I do this right? And it adds up to 27.5? Yeah. Okay, so you must have just made a careless mistake, but good for checking it. And now you know that this has to add up to 56. Okay, now, so we can use the z-test again to test the null, since we have, just the same way we did before. And the expected value of UA is just going to be, as we just said, the expected value of UA is going to equal, well, there's just half the pairwise comparisons. Because think of it, that's what you would expect. If the 2 groups are just under the null, there's no difference, right? That the 2 groups, the 2 exams are the same. It's just like, there's just random variation. So if you you'd expect the scores for both teams to be the same, right? Half the pairwise comparisons. They'd lose half their matches and they'd win half their matches. So that's the same for both. And the standard error is the same as we had before. So that's going to be the same standard error because, well, so it's going to be exactly what we had before. The standard error for both groups is still 7 times 8, just what we did before, times 16 over 12, and we get 8.64 again. And note that this is exactly the same errors that we had before, and it's not surprising because they really just differ by a constant. The easiest way that I think about this and remember it is imagine when Group A has all the lowest numbers, they had all 7 of the lowest scores, then nobody on that team would be, everybody would have a U of 0, so their sum would be 0. And when that was true, their rank, what would their rank be? Their rank would be the numbers 1 through 7, which would be 7, which would be 7 times 8 over 2, 28. So they would differ by 28 there. Does that make sense? We can check that out. You can check that out and see if you add 28 to this, do you get 56.5? Yes. And if you add the numbers, how many numbers are there here? Here, if you added, now you have NB, excuse me, so you would have, instead of the numbers 1 through 8, you'd have 1 through 9 for this one, right? No, excuse me. You have 8 numbers here, right? So you'd have 36. So if you add 36 here, 36, if this is now 7. Now 8 times 9 over 2. So you'd have 36. And if you add 36 to that, you should get 63.5. Yeah. So they differ by a constant. So that's why they're going to have the same standard error. All right. So now we're going to calculate the same thing way we did before. So we get what? 20. What's our observed? Our observed is 28.5 minus our expected, which is 28. This is for Group A, all over 8.64. So again, you can see we have the same exact z-score. The numerator is just 0.5 over the same standard error. So it's just another way of calculating this. So this is the same as previous page. So of course you're going to have the same graph here. Ta-da, ta-da. And you have a 0, 1, 2, 3. -1, -2, -3. And then if I did it as a U instead this time, then the expected value is 28. And this right here is 28.5. All right? And you still have the 4% in the middle, and So we're still going to have a P of 96. It'll be the same. So our P is 96%. Yeah. And a conclusion's the same. Don't reject the null. Of course don't reject the null. These groups are very similar. 96% chance we'd get this big a difference just by the luck of the draw. And now we're going to compare the ZB to ZA, so we can do exactly the same thing. So for ZB, what would we have? We'd have our observed, which is 27.5, minus our expected. It's the same. Our expected value would just be would be exactly the same. It's the same as that. And so, and then we'd have the same standard error. So again, we just get the opposite, z-score. And the same p-values. So we can say ZB is equal to the opposite of ZA. And the U and they yield exactly the same z-scores. The advantage to the U is when we turn the page, you can see that the tables, because I guess just because they're smaller numbers, U statistics are smaller numbers, so that they made all the tables in terms of U. Actually, in terms of the lowest U. So that's just the way the tables are built. This is the exact probability distribution. And so let's look at what we need to do here. So because it's the lowest, so this is for p-value of 5%. And I mean, you could, it's not that hard calculating the exact probability distribution if you have really small samples by hand, but it's more convenient to use these tables. So this lists the critical values. And the convention is they have this N2 and N1, and this is the, N1 is the smaller sample size, and this is the bigger sample size. See, this is what it says here. And these are the critical values for the smaller U-stat. So remember, the U-stats are supposed to, when under the null for each group, they'd be about the same. If you look at if you look at the little one, then you'd reject the null if it was even smaller than the one listed here. So if we were looking at the bigger one, of course, we'd reject the null if it was even bigger. But the way the tables are set up, okay? So what do we do here? So we have our bigger sample size is 8. So we're going to look right here with our bigger sample. You can read the directions. I'm just paraphrasing them. 8, and then we go to 7, and we go across, and there is our critical value. So our critical value at 5% for two-tailed is equal to 10. So that means in our U-stat, the smaller U-stat, go with the smaller one always, that's what we're using here. Our U-stat, our smaller one, is 27.5. So we can't reject the null. We know that already. What would we need? We'd need the smaller U-stat to be less than 10 to reject null at 5%. For the two-sided. So for example, we have a small sample size. Sometimes the sample size is too small to even reject the null, because even if all the low scores were in one group and the high scores were in the other, you wouldn't get a big enough stat. You see, you need a certain, they don't even list them for small groups, really small groups. But let's say, what's the smallest U we could get? Rearrange the exam scores to find the U-stat closest to the critical value closest to 10 without going over. Let's just start. You can do that on your own. I want you to play around with it, but let's find what would be the smallest U-stat. If we rearrange the scores so that we put all the lowest scores in this group, then we can do that. So if we put we start off, this is 11, and then we'd have the next lowest is 60, then 65, then 70, then the other 70, 1, 2, 3, 4, 5. I need 2 more, 75 and 79. Okay, so let's say we got the most extreme, the most unlikely extreme. So this exam, group A, this exam A was so much harder. Look at all those lowest scores. Everyone in this group scored lower than everyone in the other exam. So the other one would start at 81, then it would be 85, then 88, then 90, 92, 95, 96, and 100. 1, 2, 3, 4, 5, 6, 7, 8. Can you imagine what that would be like if I wrote 2 exams in everything, and this is what it looked like? I know for sure there's got to be something terribly wrong here. These are not the same. This would be insane, right? But anyway, let's just figure out what the U statistic would be. Of course, what would the U be? For each one of these, nobody beats anybody here. These people bombed it. compared to this group. I mean, this one's close, but didn't beat anybody. So the total U count, the lowest possible, would be 0. And of course, here, everybody, in terms of just the U, everybody did just as well. They all beat the other group. So they all beat 7. So add them together, and there's 8 7s is 56. And of course, it adds up to 56. So yeah, we'd reject the null here, but I'm asking, what other arrangements can you make? So this is the smallest possible. So my question is, okay, to find the critical value listed without going over. Closest to 10 without going over. Well, here we got 0, our small one 0. So I want to just see, can you rearrange it so you get 10? Exactly 10? Try that, see if you can. There's probably multiple ways you can do that. Or see how close you can get. See if you can get 10. So that'll just be, I think it'll just help you play around with it. There's not just a single solution, just switch some of these. Switch some of the, maybe try switching one, what happens? That wouldn't be enough. If you took the highest, it wouldn't be enough. You'd have to maybe switch 2 of them. Right? Yeah, you can't just switch one of them. So it's just fun to play around with. And then that's all we'll do. How about do you want to stop there? And that's enough for you guys to do your homework.